Hello everyone, I am Ramesh Paul, a PhD student at Indian Institute of Science, Bangalore. Today I'll be talking about my work titled Independent Sets in Semirandom Hypergraphs. This is a joint work with Yash, Khanna and Anand Lewis. Let me start with a brief outline of the talk. I start by motivating these semi-random models in which we study this problem. Then I'll talk about an important work abbreviated as MMT20, which solves this problem in graphs. Then I'll talk about our extension of these results to hypergraphs. And I'll end with a couple of open problems in this area. So hypergraph is a set system which consists of set of vertices shown in blue here and set of edges shown in red here. So this is an example of a three uniform hypergraph since every edge spans three vertices. Now a set of vertices in this graph would be an independent set if no edge is completely contained inside the set. So in this toy example, one can check that the maximum independent set has cardinality 5 and we show one such set here. However, in general, the problem is NP hard. Uh, in fact, even the degenerate graph version of the problem is NP hard. But not only that, the problem is abysmally hard in the sense these results by Hostal and Zuckerman show that one cannot obtain a better approximation than n to the power 1 minus epsilon for any epsilon greater than 0 unless p equals to n. Now, given such intractability, it's natural to consider easier instances of the problem. And the idea there is to progressively robustify these instances and sort of build towards the worst case instances of the problem. So this is an approach which is taken by this area, which is called beyond worst case analysis of algorithms. And there are many frameworks which consider these kind of approaches. A popular one is the area of parameterized algorithm. Then there is perturbation resilient instances, smooth analysis, and the one that we consider in our work, which is the random and semi-random models. And for a more details on such models, we refer to this book by Tim Garden. In this talk, we'll talk about these random and semi-random models, which is a probabilistic hierarchy of model where we progressively weaken the assumptions. So we start by considering these random planted models where we plant a hidden structure, like in our example, an independent set, on a subset of vertices S of size k. This is shown by these green vertices here. And the rest of the graph is chosen randomly, which means that we add an edge between a pair of vertices with probability p independently, shown by these dotted orange edges here. And now the algorithmic task is to try to recover these planted set of vertices. These models try to capture the motif that real life instances have such an optimal solution which can act as the planted solution. Like you are trying to run clustering on a data where you expect to find clusters. Now for our independent set problems in graphs, we can use some concentration techniques and spectral techniques to recover in these under these models for a planted set as small as square root n. However, since these models are not very realistic, these algorithms also tend to be brittle on real life instances. So the next step up towards robustifying these models is these semi-random models, which is a hierarchy of models where we allow an adversary to interact with the graph. However, as such, we cannot allow an arbitrary adversary since it can convert the instance into the worst case instance where we know the problem is abysmally hard. So we restrict the adversary by saying that firstly it should respect the planted solution. And then we only allow monotone adversaries which can only do monotone operations on the graph, which means that it can either only add edges to the graph or only remove edges from the graph, but not both the operations. So algorithms developed under these models are more robust and these tend to generalize well on real life instances. And interestingly enough, for many of these semi-random models, we can recover the planted independent set for k as small as square root n using some SDB based techniques. On the extreme end of these semi-random models is this Feige-Killian model, which is a very strong semi-random model. In this model, we start with these dotted edges, which is the random edges between S and V minus S. But this is the only randomness that we use. So the V minus S, which is like a large part of the graph, is empty to start with, and we allow an adversary to arbitrarily add edges in this portion. So this is shown by these pink edges here. And also we allow an adversary to arbitrarily add edges between S and V minus S on top of the random edges that we started with. And now we try to recover this graph. So you can see that we're really stretching the notion of an easier instance in these kind of models. And we're really pushing it towards the worst case instances of the model. And of course, this is the view that the algorithm sees, and now it must recover the green set of vertices. However, the way we have defined the notion of recovery so far, it seems impossible to recover for k equals to small of n in these kind of strong adversarial models. Because if k is less than n by 2, then the adversary can plant an even bigger independent set in V minus S since it has entire control over that part of the graph. So this is where, so something needs to be relaxed somewhere. And this is where the work by Mackenzie, Mehta and Trevisan comes in, which says, which studies this problem in this Fagin model for graphs. And it says that you can get an algorithm which does not return the exact planted set, but returns a large independent set of size 1 minus epsilon times k, but for k of order n to the power 2 by 3, which is smaller of n. So it's not square root n as we had in the other models, but it's still n to the power 2 by 3. This result is based upon ideas of crude SDP and SDB bonding, which I'll get to next. So the crude SDP is a very nice idea by Kola, Makarichev and Makarichev. But the idea in a nutshell is that we focus on the optimizer instead of the optimum. So while in a typical SDP, the objective function tries to relate to the problem, in a crude SDP, what we are more interested in is the configuration of these vector decision variables. So as can be seen in the intended solution as well, we're trying to map all the vectors corresponding to the planted set to a single vector. So we're trying to cluster these together and trying to make the vectors which have edges as far away from each other as possible. So the hope is that the in the end, after optimizing this SDP, the optimizer would end up looking something like this, where the vectors correspond to the set S are clustered together. And now we can just take a ball around vertex and capture small ball around a vertex and capture the corresponding neighbors and return that as the planted set. To make this formal, the, for analysis, they consider this SDB bounding technique, where they take this objective function and show that it can be broken up into three portions, one which comes from the part S, one which comes from S cross V minus S, and the third one, the contribution from V minus S. And they show that the most of the contribution comes from the first term, since the second term is corresponds to the random part of the graph. Recall that the only randomness in the model was between S and V minus S, and that can be bounded using spectral bounds for random matrices and growth and decay inequality. And the third part is using this their cleverly constructed intended solution. They relate it to the optimum solution and just get rid of that. So now I'll talk about our extension of these results to our uniform hypergraphs. Similar to the graph case, we'll also use a crude SDP here. However, we augment this with R levels of lesser sum of square hierarchy of constraints. Here we add decision variables for tuples up to size R, and we add the corresponding lesser sum of square constraints on these variables. Instead of k equals to n to the power 2 by 3, we can only recover for this value of k now. But this is fine because this is still small of n. Now these kind of higher order SDPs have been considered for the worst case instances of the problem, but this is not what we are interested in. We want to generalize the crude SDP that we wrote earlier to the R uniform hypergraph case. And for simplicity, let us take R equals to 3 case. So the SDP on the right hand side here is a natural extension of our crude SDP to the 3 uniform hypergraph case. But this is not going to be enough because we need these additional constraints, these lesser sum of square hierarchy of constraints. And we'll add them using their probabilistic interpretation, which I'll explain using this example. So say n is equals to 4, and we have this tuple x1 to 4. This can now be thought of as an event where x1 is 1, x2 is 1, x3 is 0, and x4 is 1. Now, as such, there need not be any distribution which satisfies this. However, what can be shown is that if we are only interested in computing probabilities of up to r events, then these form a consistent distribution. So using this, we can extend our SDP. So note that we have added a bunch of constraints now. So the second last constraint here can be thought of using this probabilistic interpretation, that a probability of a sub-event is more than a probability of an event. Similarly, this last constraint can also be thought in a probabilistic fashion. It can be thought of as a union bound on the complement of event given by these tuples. So this way we can generalize for any value of r. So there is an additional challenge in the SDP bounding step, where this middle term, which earlier corresponded to a random graph, now corresponds to a random hypergraph, and it's not clear how we'll bound these terms corresponding to the random tensor. So here we use a construction which converts this random portion on the hypergraph at the boundary of S to a random bipartite graph on n to the power r minus 1 vertices, and we can again use the spectral norm of random matrices to bound this term. Now I'll talk about a couple of open problems in this area. So firstly, in the graph case, we saw that this Faggy-Killian model, the paper MMT20, gives a recovery for n to the power 2 by 3. But in the other semi-random models, we could recover for square root of n. So there is some gap that can be bridged here. Also, to the best of our knowledge, the hypergraph case, there is still open if we can get recovery for k equals to square root of n in even these weaker semi-random models. Also, harnessing the power, the full power of this Lesser sum of square paradigm is something that remains to be seen in the approximation community. Thank you.